So today we will continue with our examples and applications of Sylow theorems, and we start with an interesting one. Show that there is only one group of order 1001. This is unlike the other examples we did, which ask you to verify that the group is not simple, or ask you to find a specific normal subgroup. So let's continue with a proof. And of course, what is meant here by only one group is that one group up to isomorphism. Otherwise, there are millions of groups of order 1001. So let's assume that our group G has order 1001, and we take prime factorization of this order, which gives us 7 times 11 times 13. Okay. Now we look at the Sylow P subgroups. First, we have subgroups of order 7, and the number of such subgroups is n sub 7, which is congruent to 1 mod 7. That is n sub 7 equal 1 plus 7k, where k is the non-negative integer. Okay, and n sub 7 divides m, and in this case m here is 11 times 13, so it divides this number, and this gives options for n sub 7 only to be 1, 11, 13, and their product, which is 143. This is the only divisors of 11 times 13. Okay. Now you can quickly verify that the only valid option here is n sub 7 to be 1, because this is the value of k equals 0. For any other value, if you take k, for example, equal 1, that gives you 8. It does not divide any of these numbers. And if k is 2, this gives you 15. You already passed 11 and 13. And for any other options, of course, it needs to divide 143, of which the prime factorization is 11 times 13. So it must be one of those, and this cannot be obtained from any value of k. Okay. Now we have also the number of Sylow subgroups of order 11. So n sub 11, that's equal 1 plus 11k, and n sub 11 must divide n sub 11 must divide 7 times 13. So it should be one of either 1 or 7 or 13, or their product, which is 91. Okay. Again, you can quickly see that n sub 11 is also 1. So n sub 11 must be 1 by just testing the values of k. This is becoming a routine verification. So I have here n sub 11 equal 1. And similarly, n sub 13 equal 1 plus 13k, and n sub 13 is either one of either 1 or 7 or 11 or 77. Okay, and this also gives us n sub 13 to be 1. Okay, so we have unique Sylow B subgroups of order 7, 11, and 13. So we can assume we have subgroups, which is normal according to the theorem we proved last time. So this means they exist normal subgroups. Let's call it H, K, L. All are normal in G, where the order of H is 7 and order of K 11 and order of L is 13. Okay. Now we look at the relationship of these subgroups together. Now if you look at the intersection of H and K, okay, so H intersection K, H and K are their orders are co-prime 7 and 11. So the intersection can only be the identity because the intersection is a subgroup of both. So the order of the intersection must divide 7 and divide 11. The only possibility is order 1, which means we only have the identity in the middle. Then you recall a theorem from direct product that if H and K are normal in G and H intersection K is the identity, then the subgroup, then first of all HK must be a subgroup, of course, because they are two normal, but then HK is isomorphic to the direct product of H and K. Okay, so we have HK isomorphic to product of H and K, and now H is a group of order 7, so it is isomorphic to a cyclic group of order 7 because it is prime, and we can also say this is Z7, the additive group modulo 7, and K is isomorphic to cyclic group of order 11, and 7 and 11 are co-primes, so this must be isomorphic to a cyclic group of order 77, their product. Okay, so now again we have HK is normal in G, of course, because both are normal, and L is normal in G, and we have the intersection of HK and L must be the identity because any element in the intersection must divide the order of HK, which is 77, and divide the order of L, which is 13. So both are co-primes. The only possibility is the identity. And so this implies that HK L is isomorphic to the direct product of HK and L, and this is isomorphic to a cyclic group of order 77, and this is isomorphic to a cyclic group of order 13. So now again both are co-primes, so this must be isomorphic to a cyclic group of order 1001. Now we have this is the number of elements in G, so we must have G equal H K L, which is isomorphic to a cyclic group of order 1001. Okay, so any group of this order must be isomorphic to a cyclic group of order 1001, and therefore up to isomorphism there is only one cyclic group of this order. Okay, now let's take another example. Okay, let's take the case of groups of order 70. So let's G equal order of G equal 70. Okay, show that G has cyclic normal subgroup of order 35. Of course, we only have to show that it is cyclic because order 35 means it is index in G is 2, and any subgroup of index 2 is normal. Okay, so we have proof order of G equals 70, which we can write as 2.5.7. Okay, now we have the number of Sylow 5 subgroups equal 1, and the number of Sylow 7 subgroups, of course, equal 1 also. This can be verified easily. This is becoming a routine verification. So from now on, we will not much of do it in detail. Now we have, this implies, of course, you have two subgroups, H of order 5 and K of order 7. Two unique subgroups, and both are normal in G. Okay. Now this implies, of course, we have the intersection of H and K is the identity, because again any element in the intersection must divide 5 and 7, and this implies HK is isomorphic to the direct product of H and K, which is isomorphic to C5 with a direct product of C7, which is isomorphic to a cyclic group of order 35. Okay, and of course HK must be normal in G, either because both H and K are normal in G, or because the index of HK in G is 2. Okay. Now, how about the case where we cannot decide that the Sylow B subgroup is unique, okay, for either of the cases? There is very useful counting techniques which we can use for such cases, and we will see these counting techniques with the next two examples. Okay, so let's take group of order 30. Okay, question is, show that G has a cyclic normal subgroup of order 15. Okay, proof. So order of G is 30, which we can write it as 2 times 3 times 5. Okay. Now we are looking for a subgroup of order 15. So obviously we will consider Sylow 3 subgroups and Sylow 5 subgroups. Okay. Now we have the number of Sylow 3 subgroups equal 1 plus 3k, and n sub 3 must divide m. So m here is 10. Okay, and this gives option for n sub 3 to be either 1, or in the case of k equals 3, it can be also 10. Okay, no other valid options. And for number of Sylow subgroups of order 5, we have 1 plus 5k, and n sub 5 must divide m. So m in this case is 6. Okay, and this gives option n sub 5 is 1, or in the case of k equal 1, so it can be also 6. Okay, it divides 6 here. No other valid options. So here we cannot really decide whether n sub 3 is 1 or 10, or whether n sub 5 is 1 or 6. Okay, but we claim the following. Claim n sub 3 equal 1 or n sub 5 equal 1. Okay, so we cannot have a case of both n sub 3 equal 10 and n sub 5 equal 6 in the same time. So proof is very simple. By contradiction. Okay, suppose that n sub 3 equal 10 and n sub 5 equal 6. Okay, now we look at the non-identity elements in both. Okay, so here we have 10 subgroups of order 3, right? We have 10 subgroups of order 3. So the number of non-identity elements here is 2. So we have 10 times 2, okay? Plus we have 6 subgroups of order 5, and in a group of order 5 we have 4 non-identity elements. So this gives us 20 plus 24. So we have 44 non-identity elements in both. But this is greater than the order of G, right? Order of G is 30. So it is a contradiction. Okay? So we must have, this implies that n sub 3 equal 1 is either n sub 3 equal 1 or n sub 5 equal 1. Okay? So if we take the order of H to be 3 and order of K to be 5, then we will have either H is normal in G or K is normal in G. Okay? Now HK must be a subgroup of G, and this is also a known theorem that if any H or K are normal subgroups, then HK must be a subgroup, but not necessarily normal subgroup, not yet. Okay. Now, what is the intersection of H and K? It is, of course, only the identity, because any element in the intersection, its order must divide both 3 and 5. Okay. So only the identity. Okay. Now, the order of HK equal the product of orders of H and K divided by the order of the intersection. And this 3 times 5, so we have here 15, and this is only 1. Okay? So the index in G of HK equal the order of G over the order of HK, and this is 30 over 15, so it is 2, and any subgroup of index 2 is necessarily normal. So HK is normal in G. Okay, we cannot use still the idea that HK is isomorphic to a direct product of H and K, because the direct product requires both H and K be normal subgroups. Instead, we will use the following. Okay, let Q equal HK. Okay, now we look at the group Q. Okay, the order of Q equal 15, which we can write it as 3 times 5. Now we apply Sylow theorem to this group. Okay, we have the number of Sylow 3 subgroups equal 1 plus 3k, and n sub 3 must divide m which is here 5. Okay, so only 1 and 5 can divide 5, so we must have n sub 3 equal 1. Okay, and the number of Sylow 5 subgroups is 1 plus 5k, and n sub 5 must divide 3. So only 1 and 3 can work here. So we must have n sub 5 equal 1. Okay. So we have two normal subgroups because they are unique, right? But H is a subgroup in Q of order 3, and K is a subgroup in Q of order 5. Both are normal in Q by this argument. So this implies that H is normal in Q and K is normal in Q. Okay, and of course the intersection of H and K is still only the identity. So we can use now the direct product. This implies that HK, okay, viewed as normal subgroups of Q, okay, are isomorphic to H direct product of K, and this is isomorphic, of course, to C3 direct product with C5, and this is isomorphic to C15. Okay, so this implies that we have a subgroup Q, okay, which is HK, and it is isomorphic to C15, and Q is a normal subgroup of G. Okay, this completes the proof. Now let's look at one more example which add one more complication. Let's take the case of groups of order let G of order 105. Okay, so we can again, the question is show that G has a cyclic normal subgroup of order 35. Okay, so the index here of any subgroup of this order is not 2. So we cannot use this argument to say that there is a normal subgroup. The index is actually 3. Okay, but we can use other arguments. Okay, now proof. We have order of G equal 105, which we can write as 3 times 5 times 7. Okay, now obviously we are looking at groups of order 5 and order 7. Okay, now n sub 5, okay, equal 1 plus 5k, and n sub 5 divide m. Okay, and m here of course is 21. Okay, so this gives us options for n sub 5. It can be n sub 5 can be 1 or it can be 21. No other options. This can be verified easily from the different values of k. And we have n sub 7 equal 1 plus 7k, and n sub 7 must divide m, so this is here 15. Okay, and this gives us options for n sub 7 to be 1 or n sub 7 to be 15 itself. Okay, now we assume that we do not have any normal subgroups of order 5 and 7, So this means that n sub 5 equal 21 and n sub 7 equal 15 in the same time. And this implies for the number of non-identity elements that first we have 21 subgroups into the number of non-identity elements in groups of order 5, that is 4. And we have here 15 subgroups, and this is of order 7. So we have 6 non-identity elements, and this sum is 174, which is greater than the order of G, and that is 105. So this is a contradiction, and therefore we must have either n sub 5 equal 1 or n sub 7 equal 1. Okay. Now we let the group H, okay, be a subgroup of G such that the order of H equal 5, and let order of K subgroup equal 7. Okay. So it is either H is a normal or K is normal in G. Okay. Now we note that immediately that the intersection of H and K is trivial. Okay, because again any element in the intersection must divide both 5 and 7. Okay, and also immediately if H or K are normal subgroups, then we have HK to be to be a subgroup of G, not necessarily a normal subgroup. And of course, the order of HK equals the order of H times the order of K over the order of the intersection, and this gives us 35. Okay, so we already obtained a group of order 35. Now we here note also that we cannot immediately use direct product, because again we are not certain that both groups are normal. Okay, so this time instead we look at the cosets of HK in G. So we let Q equal HK, then the index, okay, of Q in G, that would be 105 over 35. This would be 3. Okay, so the number of left cosets of Q in G will be 3. Okay, so we let G act on the left cosets of Q by left multiplication. Okay, and as you know, this action induces homomorphism from Q to a symmetric group, okay, of degree 3. So they exist some homomorphism phi from Q to the symmetric group S3. Okay, now we look at the kernel of this. Of course, the kernel of phi must be contained in the Q. This is also a standard theorem from group actions. Now the kernel, okay, of phi, if we look at the order of this kernel, it cannot be 1, because if it is 1, then this homomorphism will be injective. Okay, and in this case we will have so if it is 1, let me do it here. If the order of the kernel of phi equal 1, then this phi is injective. Okay, and this implies that order of G is at most the order of S3. Okay, and this is a contradiction because this order here is 3 factorial, okay, equals 6, and this is 105. Okay, also the order of the kernel of phi cannot equal 5 or 7. Okay, and the reason is that by the first isomorphism theorem, we have the quotient group G by the kernel of phi is isomorphic to the image of G, which is a subgroup of S3. Okay, and this means that the order of this quotient must divide the order of S3, which is 6. Okay, 3 factorial. Now, if the order of the kernel of phi equal 5, this implies this order of the quotient equal order of G over order of the kernel, that is 105 by 5, which is 21. Okay, contradiction because 21 does not divide 6. So this is contradiction. And also, if the order of the kernel equals 7, this means that the order of the quotient, okay, G by the kernel, this is 105 over 7, and we obtain 15. Again, contradiction. Okay, so we have only one option remaining. Okay, since the kernel of phi is a subgroup, okay, of Q. Remember Q equal HK. Okay, then the order of the kernel of phi must be the order, okay, of Q. So it must be 35 itself. Okay, because the only options for the order of the kernel is 1, 5, 7, 35. Okay, we ruled out all the first three options, so the order of the kernel can be only 35, and this implies that Q equal kernel Q equal the kernel of phi. Okay, and this implies that Q is a normal, of course, subgroup in G. Right now we have H. Okay, is a subgroup, of course, of Q, and K, of course, is a subgroup of Q. Okay, so let's look at Q itself in view of Sylow's theorem. So we have order of Q equals 35. Okay, that is 5 times 7. Now, by Sylow theorems, and this you can verify. Okay, the n sub 5 can only be 1, and n sub 7 can only be 1. Okay, with respect to Q. Okay, so this implies that H is in fact a normal subgroup in Q, and K normal subgroup in Q. So immediately we can apply the internal direct product. This implies that Q equal HK is isomorphic to the direct product of H and K, which is isomorphic to cyclic subgroup of order 5 and a cyclic subgroup of order 7, which is again isomorphic to a cyclic subgroup of order 35, and we already seen that it is normal. So this completes the proof, and this concludes our session for today with applications of Sylow theorems.